Bismillah, this is Dr. Magda Talib Al-Hinai from the Department of Mathematics and Statistics presenting matrices. This presentation is exclusive to the Independent Learning Center at Sultan Qaboos University. We start with the definition of matrices. A matrix is a rectangular array of m by n numbers arranged in the form in front of us. We see that in front of us we have an array of m rows and n columns. This is called a matrix of order m by n, where m is the number of rows and n is the number of columns. We see in front of us some examples of matrices. The matrix A, it has 2 rows and 3 columns. We call it a matrix of order 2 by 3, while the matrix B has 3 rows and 2 columns. This is a matrix of order 3 by 2. We come to the matrix C. We see in front of us 3 rows and 3 columns. We call it a matrix of order 3 by 3 or just 3. We present now some special matrices. We start with the row vector matrix. This is a matrix having only 1 row and n columns. Usually it is denoted by A sub 1 by n. For example, we have A sub 1 by 3 is equal to minus 1, 6, 0. These are arranged in a row. Next, we come to the column vector matrix. It's a matrix having only 1 column and m rows. This is denoted by A sub m by 1. We see in front of us an example of A sub 4 by 1. This is equal to minus 2, 11, minus 5, minus 8, all arranged in 1 column with 4 rows. Here we have the square matrix, which is a matrix having the same number of rows and columns. This is denoted by A sub n by n. For example, A sub 4 by 4 is given in front of us having 4 rows and 4 columns, and this is a square matrix of order 4. Now we see in front of us the diagonal matrix, which is a matrix having all its elements 0 except the diagonal elements. We see in front of us an example for a diagonal matrix, which is a 3 by 3 matrix. We see that the diagonal elements are 5, 9, and 8. All the other elements are zeros. The unit matrix is a diagonal matrix for which all the diagonal elements are 1s. So we see in front of us an example here of a 4 by 4 square matrix. The diagonal elements are 1s, and we call it the unit matrix. The zero matrix, it's the matrix with all elements zeros. As we see in front of us, an example for a 3 by 2 matrix, which is a zero matrix. And here comes the upper triangular square matrix, which is a square matrix for which all the elements below the diagonal are 0. And here comes the upper triangular square matrix, which is a square matrix having all elements below the diagonal zeros. We see an example for a 4 by 4 matrix, which is an upper triangular matrix. We see the diagonal elements with this nice color. Below the diagonal, we have zeros, and above the diagonal, we have numbers, which are not zeros. Now, the lower triangular square matrix is the square matrix for which all the elements above the diagonal are zeros. Again, we have a 4 by 4 square matrix, and the diagonal elements having this nice color. The elements above the diagonal are all zeros. So this we call the lower triangular square matrix. Now we move to the algebra of matrices. We start with equal matrices. Two matrices A and B are said to be equal if and only if they have the same order and the corresponding elements in both matrices are the same. Here we have two examples for matrices which are not equal. In the first example, we have 2 by 2 matrices. Yes, they have the same order, but the corresponding elements are not equal. And in the second example, we have a 2 by 2 matrix and a 4 by 1 matrix. Of course, we can see that the order of the two matrices are not the same. That's why they are not equal. Now we give an example. Find the values of x, y, and z for which the two matrices A and B are equal. We see A and B, both of them are 2 by 2 matrices, so they have the same order. Now we want to set the corresponding elements equal. So 6 in matrix A corresponds to x minus 2 in matrix B. So this is the first equation we get. X minus 2 equals 6. This implies that x is equal 8. Now we go to the z plus 1 in the matrix A. This element corresponds to 9 in matrix B. And 2y in matrix B corresponds to 10 in matrix A. So when we set 2y equals to 10, we get y is equal to 5. And when we set z plus 1 equals to 9, we get z is equal to 8. So this way we found the three values x, y, and z, 8, 5, and 8 respectively. Now we want to see what happens when we multiply a matrix by a constant or a scalar. So we say let A be a matrix of order m by n and let k be a scalar. Then multiplying the matrix A with k gives us a new matrix. We call it Cm by n, which is having the same order. And this Cm by n has the element small c sub ij. The c sub ij is equal to k multiplied by the elements a sub ij for all I and j. And we'll have an example to make this multiplication clear for you. Example: if A is the 2 by 2 matrix in front of us, I read it row by row, minus 6, 4, 10, 5. Find minus A, 6A, and half A. We start finding minus A. Minus A means multiplying the matrix A by minus 1. And according to the rule we've seen on the last slide, this means that the minus 1 will be multiplied by each element inside the matrix. So now we have minus 1 times minus 6, minus 1 times 4. In the second row, minus 1 times 10, minus 1 times 5. This gives us the matrix 6, minus 4, minus 10, minus 5. Now we try to find 6 multiplied by matrix A. This means that 6 will be multiplied by each element inside the matrix. So 6 times minus 6, 6 times minus 6 times 4, 6 times 10, 6 times 5. So for this we have the 2 by 2 matrix, which is minus 36, 24, 60, and 30. Now we come to the last part of the question, which is find half A. So half A equals half minus 6, half 4, half 10, half of 5, and this gives us minus 3, 2, 5, and 5 over 2. Now we come to addition and subtraction of matrices. If I have a matrix A and a matrix B, and both are having the same order, so we define the sum or difference as A plus B plus or minus B. This will give us as a matrix C, such that we add the corresponding elements in both matrices A and B to get the C sub ij. So let's have an example to make this clear. Example: find the sum of the two matrices A, which is 1 minus 1, 2, 5, and B, which is 4, 1, 8, 7. So we start adding the two matrices. We add the corresponding elements in each matrix. So 1 in A corresponds to 4 in B. So 1 plus 4. Minus 1 in A corresponds to 1 in B. So this will be minus 1 plus 1. 2 in A corresponds to 8 in B. This gives us 2 plus 8. 5 in A corresponds to 7 in B. This gives us the element 5 plus 7. And performing addition, we arrive at the matrix of the sum, which is 5, 0, 10, 12. Another example, I'm giving you 2 by 2 matrix A and another 2 by 2 matrix B, and I'm asking for the difference. In the similar way, we subtract the corresponding elements. So 15 corresponds to 7, so we have 15 minus 7. 1 corresponds to 5, we have 1 minus 5. 9 corresponds to 0, we have 9 minus 0. 13 corresponds to 8, this gives us 13 minus 8. And we do the subtraction to get the difference matrix, which is 8 minus 4, 9, 5. Here we have some important remarks. Adding or subtracting matrices of different order is not defined. So let's give an example. We have here a 3 by 2 matrix. We add it to a 2 by 2 matrix. We cannot perform this addition. Also, I have some students asking, what happens if I add a number to a whole matrix? This is not defined, and we see in front of us an example. A 3 by 2 matrix added to 7. We cannot perform addition. One more example. If A is the 3 by 2 matrix in front of us, 7, 3, 0, 6, 4, 1, and B is the 3 by 2 matrix, 1, 3, 2, 0, 5, 1, evaluate 2A plus 3B. Now we start solving. This means we have 2A plus 3B. 2A means I multiply the matrix A by 2, and 3B means I multiply the matrix B by 3. So, and then I perform the addition. Multiplication of the matrix A by 2 gives us 2 times 7, 14, 2 times 3, 6, 2 times 0 in the second row, 0, 2 times 6 in the second row, 12, 2 times 4 in the third row of A, this is 8, 2 times 1 in the third row, and the second column of A, this is 2. Now we go perform multiplication of 3 by B. 3 times the matrix B, the first multiplication will be 3 times 1, 3 times 3 in the first row, this is 9. We go to the second row, 3 times 2, 6, 3 times 0, 0. The third row, 3 times 5, 15, 3 times 1, 3. And then we perform addition of the corresponding elements. So we get 17, 15, 6, 12, 23, and 5. Here are some properties of adding matrices. Addition of matrices is satisfying the commutative property. So when we say matrix A plus matrix B, this is equal to saying matrix B plus matrix A. And here in front of us, we have a nice example to illustrate this. The second property is the associative property. So we have addition of matrices satisfying this associative property. Also here we have an example to illustrate that adding matrices satisfies the associative property. We have the zero matrix, which is the identity of addition. So when I add a matrix to the zero matrix, I get the matrix A. So if I have 1, 3, 2, 7, I add to it its zero matrix, so it will be a 2 by 2 matrix. All elements are 0. So 1 plus 0, again I get 1. 3 plus 0, I get 3. 2 plus 0, I get 2. 7 plus 0, I get 7. So this is the identity of addition. There also exists an inverse matrix for addition. So if I consider the matrix A, B, C, D, and the matrix minus A, minus B, minus C, minus D, and I try to add these two matrices as we see in front of us, we see that A corresponds to minus A, they add up to 0, and B corresponds to minus B, also their sum is 0. C corresponds to minus C, they add up to 0. D corresponds to minus D, their sum is also 0. So adding the matrix to the inverse matrix of addition, we get the zero matrix.